Okay, so we're going to work through an example here of this frame. It's got a couple multi-force links and a couple two-force links, two-force members, and it's got this it's pinned at both sides, and is it's got that 600-pound force pushing at it from the side. So went and just redrew our situation here. Made one change. I replaced this I replaced GF on the diagram from the book with G here, so just so we don't confuse which F we're talking about, whether F is referring to forces in general or if F is referring to that location. It's annoying, so I'm going to try to avoid using F as a spot from now on whenever I remember to do so. So anyways, so we got that force applied. Trying to find what the reactions are, and we're trying to find the forces in the members AB and CD. So those two are two force members. You'll note that you know, on our drawing here, these ones here, they've just got two pins. They don't have any loads applied at any points other than that. I mean, you could consider that the only one that has a load applied at a joint it's connected to is A here. It's got that 600-pound force there is applied at the joint between these two members, but it's applied at the joint, so that's fine. It's not going to affect things. If it was applied, say, I don't know, here, then that would be an issue. That would not be a two-force member anymore. But it is, so we don't need to worry about that. And of course, ACE and BDG are all multi-force members. So just drew a free body diagram here of the overall frame. So we've got the one load, and because it's pinned at both sides, we've got two sets of reactions. So it's 4 unknowns, and we've only got 3 equations. So we can't solve the entirety of this question at this point. But we can get kind of close, though. What we would be able to do is essentially solve for 2 of them at a time. So what we can do is we can take a moment about E here. Then we can solve something here. So we'll see what we get here. So taking the moment about E, we've got this 600-pound force times the 10 feet between there and there. That's 10 feet. 600 times 10 feet, and that's a negative value. I know my pencil mark didn't quite show up too well, but that's a negative value there. Because again, that'll be causing a clockwise rotation about this point. And then we've got the other forces. EX passes through E, EY passes through E, GX its line of action passes through E as well. So we don't include that in our moment calculation. So the only other one that shows up is this GY, and so it's GY separated by 6 feet. So 6 feet times GY, and again, as opposed to this other one, that'll be prompting a counterclockwise rotation. So that'll be a positive moment when taken about E. So we can use that to fairly easily solve for gy. Gy is equal to 1,000 pounds force. And then, simple enough, next thing we need to know is, next thing we can do is we can take the sum of the forces in the y direction. There's just the two of them, so 0 is equal to gy plus ey. If gy is 1,000, then ey needs to be a negative 1,000 pounds. So, we got two of our things there. We're getting there. So, now we can't we don't have enough information to solve for our EX and GX at this point. So what we're going to have to do is we're going to have to break up our frame, and we're going to have to look at them separately. So what we're going to do is we're going to start by looking at this bar here, ACE. I'm going to zoom in a bit more here. Zoom in a bit more here. Okay, so we've got our ACE bar. I guess I'll draw the points on there too. ACE. And then we've got the forces applied to it. So we already know we have 1,000 pounds going downwards. We have 600 pounds going here. And then we have the forces from these two links. So FAB and FCD. Now again, I'd like to point out that I'm working with my default assumption that if we have a two-force member, we're assuming initially that it is under tension. And if it ends up being under compression, then we will get a negative value for whatever force we solve for that. But we always want our positive values that we calculate to denote a tensile force in that two-link bar, and in that two-force member. We got those, and then obviously just the EX that's here. So again, now we're looking at the free body diagram of just that member. So we got 3 unknowns, and we got 3 equations, which is perfectly solvable. So one thing we're going to want to do here is kind of define the directionality of those links. So they're the same size, so their length overall can be just calculated using Pythagoras' theorem. That's 6.5 feet. And then we can just define the vector force in terms of the magnitude of the forces and their I and J components. So they're both going to have the same I component, and they're going to have equal and opposite J components to their unit vector. That isn't saying that the actual forces are going to be the same. They're just, you know, they're angled. They're angled basically the same amount up or the same amount down. So it's the unit vectors. The unit vectors equal there. Not necessarily the forces. So simple enough. So we're going to take a moment about E. So taking a moment about the bottom here. So again, we got the 600 pounds. Let's use red here, or fuchsia. 600 pounds times the 10 feet. Again, clockwise. That's a clockwise rotation when taken about E, so that'll be a negative amount. And then we've got our FAB as well. So we're not worried about the vertical component of that because that doesn't cause a moment. We're only worried about the horizontal component of that. So I'm going to go ahead and worried about the horizontal component of that. So it's I portion, the 6 over 6.5 times this FAB, and then again times the 10 feet offset between here and here. And then again, that one is also a negative value. And then same deal for our FCD. We're still only worried about the vertical component and its horizontal. Sorry, we're only worried about the horizontal component, and its vertical offset is the 2.5 feet from E to C. So again, all those would be negative values if we were right, if the initial assumption that both FAB and FCD were negative is correct. That's obviously not going to be the case because then we'd be taking 3 negative values, adding them together and expecting to get 0. Ain't going to happen. So at least one of FAB or FCD needs to be positive. Needs to be compressive. But we can't quite solve for that at this point, but we can break it down to solving for one of them. So we can solve for FCD in terms of FAB. Just doing a bit of algebra here. FCD ends up being negative 2,600 pounds minus 4 FAB. And that's it for our moment calculation. So we can't do much more else with that. So next up, we're gonna just take the sum of the forces in the y direction. So we already know one of them. We got the minus 1,000 pounds, and then we've just got the vertical component of our FCD and our FAB. So again, FCD, let's clear this out a bit. So FCD, again, if it's in tensile, is angled upwards. So the vertical component is going to be positive, whereas FAB, if it's tensile, is angled downwards, so its vertical component is going to be negative. Just based, and the how much is based upon that unit vector that we already calculated. So we can do a bit of algebra. We can solve for that. That gives us 2,600 pounds is equal to FCD minus FAB. And then we can take this FCD that we calculated for here, plug it into there. That gives us 2,600 pounds is equal to minus 2,600 pounds minus 4 FAB, and then minus another FAB. So we get 5,200 pounds is equal to negative 5 FAB, and then we just solve for FAB. That ends up being 1,040 pounds compression, negative 1,040 pounds. So that is a compressive force within this bar. And then we just need to take that value that we solved for FAB and then plug it into the formula that we already had that related FCD and FAB. So FCD is equal to negative 2,600 minus 4 FAB. So negative 2,600 minus 4 times negative 1,040 ends up being a positive value of 1,560 pounds force. So FCD is positive, so that link CD there, that is in tension. All right, so we got that. And that's we're just missing one of our unknowns in ACE. So we got this value. We got this value. We're looking for EX here. So take the sum of the forces in the x direction, that's equal to Ex plus the unit vector in the the I unit vector for FAB plus the I unit vector for FCD plus the 600 pounds pounds force. That's the load. Now I'd like to emphasize here that despite the fact that I know one of these is negative, one of these is positive, I'm not I'm keeping it in terms of adding those values based upon the directionality of what I originally drew. Oh, that was supposed to be an eraser. Based upon the directionality of what I originally drew on this diagram. I don't want to start flipping signs at this point. I don't want to start flipping the directions of the arrows before I'm done. So I will base this calculation based upon what I drew, and then just plug in a negative number for the value that ends up being negative. So we end up being able to solve for Ex. It ends up being a negative 1080 pound-feet. And then once we have that, we can just go back to our overall free body diagram. And we are able to, well, we know all of these except for this one. So easiest way to solve for that one would be just to take the sum of the forces in the x direction. So that's equal to 0, which is equal to 600 pounds, plus that, minus 1080 pounds, or 1,080 pounds, gives us a value of that reaction there being 480 pounds, again in the x direction. It's positive, so the initial guess there was correct. And that's basically how we go about doing that. So again, just try to be as consistent as you can while you're going through about your sign conventions. Don't go switching stuff halfway through. Pick a method that you're going to be using when you want to solve these, and stick with it. And you'll be good to go.